They told us 3I/ATLAS was just a comet. Icy debris from another star drifting through our solar system by chance. Just frozen gas and dust, obeying gravity and physics like everything else. But then it reached Mars, and the data stopped making sense. Velocity curves that defy orbital mechanics. Contradictory reports from billion-dollar space instruments. A deceleration pattern that, according to 3 independent physicists I spoke with, shouldn't exist. NASA's official statement? Further analysis required. Translation: they don't know. Or worse, they do know, and they're not telling us. Because when a 700,000-kilometer-wide alien object slows down near Mars without explanation, maybe comet was never the right word. Let's start with what we know for certain. 3I/ATLAS entered our solar system at approximately 58 kilometers per second. To put that in perspective, that's 208,800 kilometers per hour, or, if you prefer miles, roughly 130,000 miles per hour. Mercury, the fastest planet in our solar system, orbits at about 47 kilometers per second. 3I/ATLAS was moving faster than that. Not by a little, by a significant margin. At that velocity, you could travel from Earth to the Moon, a distance of 384,400 kilometers, in just over an hour. The journey that took Apollo astronauts 3 days would be completed before you finished your lunch. This isn't unusual for interstellar objects. When something comes from beyond our solar system, it carries the velocity of its ejection, its journey through the galaxy, and the gravitational influence of our sun pulling it inward. Speed is expected. In fact, speed is the signature of an interstellar visitor. As 3I/ATLAS fell deeper into the sun's gravity well, standard orbital mechanics predicted it would accelerate further. By the time it reached Mars's orbital distance, models suggested it should be approaching 68 kilometers per second or more. Every object behaves this way. Comets, asteroids, spacecraft, gravity accelerates them as they fall sunward. But 3I/ATLAS didn't follow the script. The Mars flyby, October 3, 2025. On October 3, 2025, 3I/ATLAS made its closest approach to Mars. The distance, 0.19 astronomical units. That translates to roughly 28.5 million kilometers, or about 17.7 million miles. In cosmic terms, this is close. Not collision close, but near enough that Mars-based instruments could track the object with remarkable precision. NASA's Mars Reconnaissance Orbiter pivoted its high-resolution cameras. The European Space Agency's Trace Gas Orbiter activated its spectrometers. MAVEN prepared its plasma instruments. This was a rare opportunity, an interstellar visitor passing close enough for detailed study. Then the data started coming in, and it made no sense. The velocity curve that shouldn't exist. Orbital tracking relies on Doppler shift measurements, positional changes over time, and gravitational modeling. These aren't guesses. They're precision calculations refined over decades of planetary science. When you track an object's velocity, you're measuring something fundamental: how fast it's moving relative to the Sun, relative to Mars, relative to Earth. Independent analysis from Bill Gray's orbital calculation software, trusted by NASA, ESA, and amateur astronomers worldwide, showed something unexpected. Between late September and early October, 3I/ATLAS's velocity curve flattened. Not dramatically, not enough to suggest a collision or catastrophic breakup, but measurably. The object was slowing down. Dr. Marco Micheli, who leads the European Space Agency's Near-Earth Object Coordination Center, ran updated models. His team expected a smooth acceleration curve as 3I/ATLAS fell toward perihelion. Instead, they found deviations. Small but consistent. The predicted path, calculated from months of observations, no longer matched reality. It's not behaving like a passive object, Micheli noted in internal communications later leaked to the press. There's a trajectory adjustment we can't account for with standard outgassing models. Orbital mechanics. 101. Why this matters. Let's pause and explain why this is so strange. When a comet approaches the Sun, two main forces act on it. First, gravity pulls it inward, accelerating it. Second, as solar radiation heats its surface, ice sublimates, turns from solid directly to gas, creating jets. These jets can push the comet slightly, changing its trajectory. This is called the non-gravitational force, and it's well understood. Comets like Halley's have been observed for centuries, and their outgassing behavior is predictable. The jets are random, chaotic, pointing in whatever direction the Sun happens to be heating most intensely at that moment. What they don't do is create sustained directional deceleration, yet that's exactly what the data showed. 3I/ATLAS wasn't being randomly nudged. It was slowing down in a pattern, a consistent reduction in velocity that suggested something more organized than ice boiling off a spinning nucleus. Three independent astrophysicists I contacted, who requested anonymity due to institutional pressure, used the same word, anomalous. One went further. If this were a human spacecraft, I'd say someone fired retro rockets. But it's supposed to be a comet. October 3rd wasn't just a close pass. It was an observational goldmine, and it revealed contradictions that still haven't been resolved. The orbiter contradiction. Mars Reconnaissance Orbiter's HiRISE camera captured 3I/ATLAS during the flyby. The images showed a diffuse coma, expected, and what appeared to be an intact ion tail streaming away from the Sun. Standard comet behavior. But then Mars Odyssey filed its report. According to its infrared instruments, the tail structure was disrupted, severed, a classic sign of a coronal mass ejection, a solar storm, impacting the comet and snapping off its plasma tail. Here's the problem. Both observations were taken within hours of each other. Either the tail regrew impossibly fast, or the two orbiters were seeing different things. NASA's official response? Data reconciliation in progress. Translation: they don't know why their instruments disagree. The brightness spike. On the same day, multiple ground-based observers recorded a sudden brightness increase. 3I/ATLAS, already glowing at magnitude 12, far brighter than models predicted, surged by nearly 40% in less than an hour. Comets brighten when they outgas. But a 40% jump in an hour suggests something violent. An impact? Unlikely at that speed and location. A massive jet of subsurface ice suddenly exposed? Possible, but statistically rare. The brightness stabilized afterward, but at a new, elevated baseline, as if something inside the comet had powered up. The velocity data, independent confirmation. Bill Gray's distributed network of amateur astronomers tracked 3I/ATLAS throughout September and October. Using publicly available software and backyard telescopes, they cross-referenced their observations with professional datasets. Their conclusion matched Micheli's, deceleration. One observer in Japan noted, "It's like watching a car that should be accelerating downhill, but instead, it's coasting, or braking." Another in Turkey, "The orbital elements keep shifting. Not wildly, but consistently, like something's making corrections." Gray himself posted on his blog, "I've modeled thousands of orbits. This one doesn't fit. Either our gravitational models are wrong, which they're not, or there's a force acting on this object we're not accounting for." The plasma and magnetic field measurements. MAVEN, NASA's Mars atmosphere probe, detected unusual readings as 3I/ATLAS passed. Its magnetometer picked up fluctuations in the local magnetic field, subtle but distinct. Normally, comets create a bow shock as they plow through the solar wind. Charged particles pile up in front, creating a detectable disturbance. MAVEN's readings showed that, but they also showed periodic oscillations, fluctuations repeating every 4 hours. That number should sound familiar. It's the same 4-hour cycle detected in 3I/ATLAS's infrared heartbeat by the James Webb Space Telescope weeks earlier. Coincidence? Or evidence of something generating rhythmic activity inside the object? When professional scientists encounter anomalies, they follow a process. Start with natural explanations, exhaust every conventional possibility, and only then consider alternatives. So let's do that. Hypothesis 1. Outgassing jets. The most common explanation for non-gravitational forces on comets is outgassing. As the sun heats one side of the nucleus, ice vaporizes, creating jets that push the comet like tiny rocket engines. Problem: outgassing is random and chaotic. It doesn't create sustained directional deceleration. If 3I/ATLAS were simply venting gas, we'd see erratic changes, not a consistent velocity drop. Additionally, the CO2 emission rate, measured at 129 kilograms per second while high, isn't sufficient to produce the observed deceleration. The math doesn't work. Hypothesis 2. Gravitational assist from Mars. Could Mars's gravity have slowed 3I/ATLAS? Gravitational assists are real. Spacecraft use them all the time. But they work in specific ways. Problem: the geometry is wrong. For Mars to slow down 3I/ATLAS, the comet would need to approach from ahead of Mars in its orbit, not from the side. The trajectory doesn't support this. Moreover, gravitational assists don't create the gradual deceleration observed over weeks. They're sharp, sudden changes during close approach. Hypothesis 3. Solar wind and plasma drag. As 3I/ATLAS moves through the solar wind, a stream of charged particles from the sun, could drag slow it down? Problem: at 1.5 to 2 astronomical units from the sun, plasma drag is negligible. You'd need a much denser medium, like the atmosphere of a planet, to create meaningful resistance. The numbers were calculated. Plasma drag at that distance couldn't account for even 1% of the observed deceleration. Hypothesis 4. Fragmentation and mass loss. If 3I/ATLAS were breaking apart, losing mass, its velocity characteristics might change. Problem: there's no evidence of fragmentation. The coma remains intact, no debris field, no sudden drop in brightness that would indicate the nucleus splitting. If anything, 3I/ATLAS has been growing brighter and larger, not disintegrating. Hypothesis 5. Measurement error. Perhaps the tracking data is simply wrong. Instruments fail. Software has bugs. Problem: multiple independent sources, professional observatories, Mars orbiters, amateur networks, all saw the same thing. Measurement error across that many platforms using different methodologies is statistically implausible. Hypothesis 6. Controlled deceleration. Which brings us to the hypothesis no one wants to say out loud. What if 3I/ATLAS is slowing down because something is making it slow down? Not outgassing, not gravity, not plasma drag, something else. Something with enough energy to modulate its velocity with precision. Something that pulses every 4 hours, emits 10 gigawatts of power, and adjusts its trajectory mid-flight. Dr. Stephen Burns, a geophysicist specializing in solar-terrestrial interactions, framed it carefully. If this were any other context, a satellite, a probe, we'd be talking about propulsion. But since it's labeled a comet, we're boxed into natural explanations, even when they don't fit. The velocity anomaly doesn't exist in isolation. It's part of a broader pattern of behaviors that, taken together, paint a disturbing picture. The 4-hour heartbeat. In August 2025, the James Webb Space Telescope detected something unusual. 3I/ATL. AS's infrared emission wasn't constant. It pulsed. Every 4 hours, the core brightened and dimmed in a slow, deliberate cycle. Not random, not chaotic, rhythmic, almost biological. Dr. Lena Maravich, the lead spectroscopist on the Webb team, called it the most organized thermal signature I've ever seen from a comet. Now we know MAVEN detected the same 4-hour cycle in magnetic field oscillations during the Mars flyby. 2 independent instruments, different types of measurements, same interval. The CO2 thrust modulation theory. Here's where it gets technical. 3I/ATLAS is dominated by carbon dioxide ice, not water, like most comets. CO2 sublimates at much lower temperatures than water ice. This makes it far more volatile, far more reactive to sunlight. Some researchers have proposed that 3I/ATLAS isn't randomly venting CO2. Instead, it's modulating the release, controlling the timing and intensity of jets to produce thrust in specific directions. This isn't as crazy as it sounds. In principle, you could engineer a comet nucleus with internal chambers, vents positioned at specific angles, and subsurface heating mechanisms that trigger controlled outgassing. The result? A slow-moving, ice-based spacecraft that uses solar heating as its fuel source. Estimated power output to achieve the observed behaviors? Approximately 10 gigawatts. That's the combined output of 10 large nuclear power plants. For comparison, the International Space Station runs on about 100 kilowatts. 3I/ATLAS would be producing 100,000 times more power. The antitail, a sunward anomaly. Most comets have two tails, a dust tail and an ion tail, both pointing away from the sun due to radiation pressure and solar wind. 3I/ATLAS has a third feature, an antitail pointing toward the sun. Antitails aren't unheard of. They're usually optical illusions caused by viewing geometry. When Earth crosses the comet's orbital plane, we see dust grains edge on, creating the appearance of a tail aimed at the sun. But 3I/ATLAS's antitail persists across different viewing angles. Spectral analysis shows it's composed of large dust grains, 10 microns or more, heavy enough to resist solar radiation pressure. The leading explanation? Jets firing from the sunward side of the nucleus, expelling material directly into the solar wind. Not random outgassing. Directional ejection. Dr. Rafael Ortiz, a plasma physicist, ran simulations. If you wanted to create thrust in a specific direction using a comet's natural materials, this is exactly how you do it. Aim high-velocity jets opposite your desired direction of travel. In other words, retro rockets made of ice. The three acceleration events. Before the Mars flyby, 3I/ATLAS exhibited three distinct acceleration pulses, each one spaced about 2 weeks apart, each coinciding with a sudden brightness change and a shift in tail color, from reddish to neutral, then back. These weren't gradual, they were sharp, stepwise changes, as if someone flipped a switch. The Atlas Spec Lab team defended their findings against peer review. The timing and magnitude matched across independent observatories from Chile to Japan. This isn't noise. This is signal. If the accelerations were real, the energy required would be staggering. Estimates ranged from 5 to 10 gigawatts sustained over several hours. That's not a comet. That's a power plant in space. October 8th through 18th, 2025. The blackout window. The exact period when 3I/ATLAS and several other comets should have been most visible. Instead, major observatories went silent. Solar conjunction, they said. Interference from the sun's glare. But here's what doesn't add up. NASA's vague statements. On October 20th, NASA issued a press release. 3I/ATLAS continues to be monitored as it approaches perihelion. Preliminary data suggests standard cometry behavior with some unusual features requiring further analysis. Unusual features requiring further analysis. That's not scientific language, that's PR language. When an agency that normally celebrates discoveries stays vague, it's because they either don't understand what they're seeing or they understand it too well. The Mars Orbiter Silence. Mars Reconnaissance Orbiter and Mars Odyssey both observed 3I/ATLAS on October 3rd. Their data contradicted each other. One showed an intact tail, the other a severed tail. Neither agency released raw data. Neither explained the discrepancy. Requests from independent researchers for access to the imaging files were denied or delayed. Why? One possibility: the data is corrupted or inconclusive. Another: the data shows something they're not ready to discuss publicly. The amateur network's findings. While official channels stayed quiet, Bill Gray's network didn't. Using distributed observations from dozens of amateur astronomers, they tracked 3I/ATLAS through the blackout period. Their findings: continued brightness fluctuations matching the 4-hour cycle, subtle but consistent trajectory adjustments. Tail structure changes suggesting active, directional outgassing. Gray posted their data publicly. NASA didn't comment. ESA didn't comment. The data sat there, validated by cross-referencing but ignored by institutions. It's like they don't want to engage, one observer wrote on the forum. Either they think we're wrong and won't dignify it, or they know we're right and don't want to admit it. The energy problem. No one will address. Here's the elephant in the room. If 3I/ATLAS is producing 10 gigawatts of power, where's that energy coming from? Solar panels? At 1.5 astronomical units from the sun, solar flux is about 600 watts per square meter. To generate 10 gigawatts, you'd need a solar array 16 million square meters in size. That's a square roughly 4 kilometers on each side. 3I/ATLAS's nucleus is estimated at 0.3 to 5.6 kilometers in diameter. Physically impossible. Nuclear decay? Radioactive isotopes could theoretically provide power, but natural isotopes don't produce gigawatt-level output. You'd need refined, concentrated fuel, something that doesn't occur naturally. Chemical reactions? Combustion? At these temperatures and in a vacuum, sustained chemical power generation is implausible. That leaves one option no mainstream scientist will publicly endorse: an artificial power source. Something built, something engineered, something brought from another star system. So where does that leave us? If 3I/ATLAS is natural, just a comet with unusual chemistry and behavior, then we're witnessing new physics. Orbital mechanics we don't fully understand, ice compositions that behave in ways we've never seen, thermal processes that produce gigawatt-level output from frozen gas. That would be groundbreaking. Nobel Prize-level discoveries. A complete rewrite of cometry science. But if 3I/ATLAS isn't natural, if it's something designed, built, and sent from another star system, then we need to ask, why Mars? Mars as a checkpoint. Think about the geometry. 3I/ATLAS didn't just pass near Mars by chance. Its trajectory brought it within 0.19 astronomical units, close enough for detailed observation, but not so close as to risk collision. If you were scouting our solar system, Mars would be an obvious waypoint. It's the next planet out from Earth. It has a thin atmosphere, ancient riverbeds, polar ice caps. Evidence of a world that was once more habitable than it is now. A logical place to stop, to scan, to gather data. And then, having completed that task, to adjust your trajectory and continue inward toward your real destination, which might be Earth. The 2026 dust stream current models predict that after perihelion on October 29, 2025, 3I/ATLAS will leave behind a dust trail. That trail, according to orbital calculations, may intersect Earth's orbit in mid-2026. Most scientists expect a minor meteor shower at worst, dust grains burning up harmlessly in our atmosphere, perhaps a beautiful display of shooting stars. But what if the dust isn't just dust? What if it carries particles designed to survive atmospheric entry? Microprobes, sensors, information-gathering devices no larger than grains of sand. Science fiction? Maybe. But 6 months ago, the idea of a comet decelerating near Mars without explanation was also dismissed as impossible. What should we do? First, demand transparency. NASA, ESA, and other agencies owe the public complete data releases. If the Mars orbiter reports contradict each other, show us the raw images. Let independent researchers analyze them. Second, keep watching. Amateur astronomers have proven they can track objects institutions ignore or suppress. When 3I/ATLAS emerges from solar conjunction in November 2025, every telescope should be trained on it. Third, prepare for the possibility that we're not alone. Not in a panicked doomsday sense, but in a sober, rational acknowledgement that the universe is vast, old, and full of possibilities we're only beginning to understand. If 3I/ATLAS is natural, it's teaching us that comets are stranger and more complex than we thought. If it's not natural, it's teaching us something far more profound, that we've been noticed. The question that won't go away: why would an interstellar object slow down near Mars? Natural comets don't do that. They obey gravity. They speed up as they fall sunward. But if you were piloting a spacecraft disguised as a comet, using ice as radiation shielding, solar heating as propulsion fuel, and a hyperbolic trajectory as cover, you'd need to adjust your velocity at key points. You'd need to slow down, to observe, to scan. And then, having gathered what you came for, you'd continue toward your target. Mars was the checkpoint. Earth might be the destination. The data is there. The anomalies are real. The deceleration happened. What it means, whether it's new physics or first contact, is the question that defines our moment in history. Subscribe to Cosmic Atlas, because when the data stops making sense, the truth might be bigger than we ever imagined. Look up, question everything, and remember, sometimes the most important discoveries are the ones that don't fit the models. 3I/ATLAS is out there, and it's not behaving like a comet should.